Okay, well, we discussed this for a couple of minutes. People had the right instincts and pretty much got it. I prompted just a little bit, but it's fairly straightforward that the concentration is, since I've got to hold still, is it 0.02 liters, I'll use an L here, over 3 liters, right? Which is approximately 0.0067 or 0.67%. So it's a 0.67% solution, right? Now, if you multiply that by the amount that flows out, you know, the volume that flows out, you're going to get how much soap flows out. Okay? So at outflow rate 0.1 liter per second, the rate at which the soap flows out is going to be 0.0067 times 0.1 liter per second. Okay? Because 0.1 liter, you know, you got water flow, you got solution flowing out at 0.1 liter per second, and 0.0067 of that solution is soap. So that should be an intuitive connection, and you want to think about it until it is. Okay? Okay? Now, in terms of the parameters of the situation up to this point, let's make a note that digression is now over. We're back to here. Okay? What are the parameters at this point? Q1, V1, and R. Okay, Q1, quantity of soap. That would be formerly our 0.02 liters. V1, volume of the container. It's not changing. 3 liters. Okay? R, the rate at which water is flowing in, being equal to the rate at which water is flowing out, or solution is flowing out, is R. And we just do the same calculation, hopefully intuitively grasping what everything means now because we did a numerical example and made sense of it. Okay? Concentration is Q1 over V1. Remember, Q1 is a function of T, and we can remind ourselves by putting the T on there any time we want to. Okay? And in many cases, V1 would also be a function of T. Like if this thing had soap in it to start with, and we're filling it, hasn't been already full, then the volume would be changing, right? And if at the same time there's a hole in the bottom and soap is flowing out, that gets to be fun. Okay? And then you got the shape of the container, and how does that affect the depth, the function at time, and all that stuff, okay? So it can get very complicated, but right now it's as simple as it can be, okay? Because we want to understand the simple case before we try to expand to changing velocity, volumes, or inflow of different amounts of soap or whatever, okay? Principles, though, are the same. Concentration is this. And even if V1 is a function of T, that would still be the constant expression for the concentration. Okay? Inflow rate equals outflow rate equals R. Right? Now the inflow is pure water, the outflow is solution. Okay? That won't always be the inflow rate and outflow rate don't have to be the same. So, we want to lay a foundation so we can build on it and consider cases where these things aren't as simple. But in this case it is. The rate at which Q1 changes was concentration times outflow rate, which is Q1 of T over V1 times R. Okay? Well, how would we then write this statement more succinctly? Well, what do we mean by the rate at which Q1 changes? How would we write the rate at which Q1 changes in mathematical symbols?
dq.
Good start, but it's Q1.
dq1.
Okay, well dq1 is a differential. Differential is not a rate.
So B.
What's the definition of a rate of change? You got to have a few more words. Rate of change of what with respect to what? What's changing? Q1 is changing, right? With respect to what? Time. So how would you write the rate of change of dq1 with respect to time?
dq over dt.
dq1 over dt. Very good. So dq1 dt equals q1, and we'll put the t on both the q1s over v1 times r. Okay? Now the only thing's a function of time is q1. All these others are constants. So what technique are we going to use to solve this equation?
I guess separating.
Yeah, we separate variables. What's the equation going to look like when we separate the variables? And it may be a good idea to suppress the t, because we've always regarded the dependence on the independent variable as implicit. Well, it's very simple, so I'm just going to write it out. Okay? Now there's one problem here. And I wrote something that's actually wrong here. I said the rate at which Q1 changes is this. Q1 is decreasing, right? So we would have to make it negative Q1 over V1 times R. It's leaving. This is the rate at which Q1 leaves. You know, the Q1 over V1 times R is the rate at which Q1 leaves, but the rate at which it changes is the negative of the rate at which it leaves, right? If my money is leaving at the rate of, let's say I'm at a carnival or something, $200 an hour, okay? I don't go to those carnivals, but you know. Okay. Then the rate at which my money is changing is negative $200 an hour, right? And if you got a couple of kids, it's really easy to lose money at that rate if you're not careful. And get a bunch of prizes that are worth, you know, 38 cents or something. Okay. Kids kind of love it, but you got to control it. So actually our differential equation would have to have a negative here, right? It's a little careless because I didn't think about that until I looked at the solution and said, well, that's not going to work. Okay? It's obvious that the rate of change of Q1 is negative. Well, that's a really easy equation to solve. Okay? We integrate both sides. The integral of dQ1 over Q1 should equal the integral of negative R over V dt. Now this is something you should be very familiar with from what you learned over a year ago in first semester calculus. And I'm sure you did it. So what's this integral?
Natural log of the absolute value of Q1.
And this is?
Negative R over V times T.
Arbitrary constant, right? So Q1, we'll say magnitude of Q1, equals e to the c, e to the negative RT over V. Now I'm not going to go through details of that, equals a e to the negative RT over V, where a has to be greater than 0. Okay? We'll say greater than or equal to 0. I mean, the case where a is equal to 0 is trivial. It means you don't have any concentration, whatever. And okay, so there we have it. A is arbitrary. And I went through the details of why A is positive, because e to the c has to be positive. But if the absolute value is this, then Q1 would be plus or minus this. So now A could be, you can put a plus or minus in front of a positive A, but when you do, you get just any A. So that's the way your constants work. And we talked about that in more detail last time. Okay, so here we have it. So let's say R is 0.1 liter per second. Volume 1 is, and of course I got to put the 1 on the volume because ultimately we've got a little bowl and a big bowl, right? With two different volumes. We want to keep that straight. And the volume of that first bowl is more like, let's see, it's about 2 cups. It's about a little more than 2 cups. We'll say it's 0.5 liters. Okay? And Q1 of 0 equals 0.03 liters, 30 milliliters, a little over an ounce of soap. Now what's this mean?
That's the original
That's how much soap I squirt in at t equals 0. Okay? Now, if later I want to squirt that soap in at some later time so I end up with equal concentrations, then it would be like Q1 of 40 equals this. At 40 seconds is when I put this in, and then I end up with equal concentrations. But of course, we're not going to know what that is when we start the problem. We're going to get a system of differential equations, which is something we'll deal with later. But we want to kind of set it up right now. We'll worry about solving it later. Okay? So we have this. Well, then we can solve it. Oh, yeah, there's my R. Okay, you got negative RT, negative 0.1 liter per second times T, divided by 0.5 liters, right? And we'll simplify that because the liters divide the liters, okay? You have negative 0.1 reciprocal seconds times t. There's your exponential function. So we can immediately graph that exponential function. We just don't know how far to make it from the axis, right? But what we do know is that the graph now is going to be a decreasing exponential, right? A decreasing exponential looks like this. So all we've got to do now is label the stupid graph, okay? And we can label the q-axis, because this is q1 versus t, right? We can label the q1 axis. We know one point on that graph, don't we? What is it?
0A.
Again?
0A.
Yeah, but from this we know, now that we know it's an exponential, we know the coordinates of one point. I mean, Q1 of 0 is 0.03 liters, right?
Yeah.
So we know that this point is 0.03 liters. And if we are clever, we also know how to find the half-life. Okay?
So is A?
It's when this numerator, this exponent, is equal to the natural log of 2. Negative natural log of 2. Okay? And if you know logarithms and exponential functions, well, you understand that instantly, but at this point, nobody expects miracles. That's pre-calculus. How could anybody know that? Okay. And it's pre-calculus at a level of mastery that we only expect from top students. We're taking a real pre-calculus student class where we don't have a bunch of students who will never understand it. Okay? And since that never happens, nobody ever comes out understanding it. Now, but you need to sort that out. Okay? Well, that means this would have to equal negative 0.7. Okay? Which means let's see if that makes sense, because I'm getting this should happen in 7 seconds. So this thing should be down to half in 7 seconds, so we get a pretty good picture of the graph. Okay? Yeah, if t is 7 seconds, I got e to the negative 1. No, e to the negative point. So e to the negative 1 is about 0.37. Okay? So e to the negative 0.7 being 0.5. Yeah, it all fits. If I had good mastery of these functions, of course, I'd know that already, wouldn't I? Okay, so anyhow, just checking myself, because I thought this was pretty obvious. So right there's a graph of my concentration. I don't have to do any heavy algebra unless I want to get more precise, right? Well, I want to get more precise because sometimes that's important. And you know, when I'm washing dishes and I don't have exactly equal concentrations, I get just paranoid. I'm afraid there's going to be diseases. I'm afraid my hands are going to get chapped. I don't know what happens, but terrible things can happen if I don't have equal concentrations. Well, not really, but in other applications, in engineering applications, yeah, it can be pretty terrible if you're off by a little bit, okay? Well, I think I got about enough uranium in this bomb. Whoops, you know, okay. Yeah, we want to be a little more careful in some situations. Okay, well, anyhow, here we got it, right? Sorry about that leg. I overdosed you with radiation, you know. Okay, so we do the analysis. Okay, well, but, you know, once we have this, we can do this, and we can get a feel for what the solution ought to be, check it against reality, see if it makes sense. It's always important for an engineer to do that. Always important for a scientist to do that, but maybe not as important for an engineer, because when a scientist screws up, it just clobbers him instead of the rest of the world. Okay? Now, okay, you got Q of 0. Anyhow. So here's what we think our model is going to look like. Let's verify it. Okay, Q of 0 should equal AE to the negative 0.1 reciprocal seconds times T. Well, times 0, right? Well, that's A. That was easy. It's not always that easy. There's always often a calculation involved. But this one was really easy to evaluate, right? Sometimes you got to actually evaluate it. Usually you do. And Q of 0 is 0.03 liters. So Q of T equals 0.03 liters times e to the negative 0.1 per second times T. If you have to go to your graphing calculator, it's pathetic. If you want to go to your graphing calculator to verify all this, it's unnecessary if you know what you're doing, but go ahead. Or spreadsheet or whatever, okay? But if you got to go to your graphing calculator to see this, it's because you don't know pre-calculus, okay? And if you got to go to a computer algebra system to solve this equation, that is pathetic. You don't know the first thing about differential equations or what anything means. All you know is here's the buttons you push to get the right answer, and you can't check that against what you know the reality to be, except by the crudest possible means, which are sometimes important. Okay, does that make sense? Well, that's easy. So now we have a way of modeling the concentration in the first bowl. And it doesn't depend on what's in the second bowl. Now what would be interesting if we had a pipe running from the first bowl to the second and a pipe from the second bowl into the first, and we were pumping water back and forth at different rates. Well, that's not hard to set up. We're not going to set up anything that complicated right now. I just want to get you used to the idea of a mixing problem. Okay? And that occurred to me this morning. I said, yeah, that's one thing I want to do in differential equations today, because I had this jar of really grossly strong green tea that was too hot to drink. Well, I was happy to dilute it because it gets less bitter. Okay, and I don't put stuff in it. So I was going to put cold water in it. So I knew that the temperature of the tea was about 140 degrees. And temperature of the water coming out of the tap this morning was probably about 40 degrees. Pretty cold last night, so the basement got pretty chilly. Might have been lower than that. So I immediately saw how much water I had to add to get the temperature down to a comfortable 115 degrees. So I could chug it down quick before I gagged on it. Okay? There are differential equations that model every aspect of that, including gagging and mental state. Okay. How committed am I? Well, I drink it every morning, so I kind of know what I'm up against. Okay, so maybe I cheated a little bit. Maybe I added a little extra water. Make it less bitter. That's the context. So in that context, I'm mixing water, okay? And that's just an instantaneous chunk of water into another chunk of water, and they mix, okay? What if I was adding water more slowly and also draining the large container? I'd be mixing, well, I'd be mixing energy, okay? Different concentrations of energy, heat. Model it exactly the same way. My quantity would be units of heat, generally measured in joules, okay? Okay, well, this tells us, and I think I lost my Q1 here, this tells us what's going into the second container, okay? And of course, that's changing every second, every instant that's changing, right? So the question becomes, how much okay, yeah, let's, so now, and by the inflow, I mean the inflow of soap. To container 2 is this, variable quantity, right? Well, if I know Q2 of T and T being the time since the first bowl got full, concentration of Q2, concentration Q2 of Q2, the quantity in the second bowl, is that over volume in the second bowl. But the volume of the second bowl is what? It's not constant. Okay? Well, what is V2 of T?
It's R times T.
Well,
Yeah.
let's get this show now. Now you know, because I'm sure what happened.
Okay?
There, baby.
So now we can begin writing a differential equation for the second. I might as well go ahead and finish. I wasn't going to, but we might as well. Because the equation's okay. We're not going to talk about how to solve it. Okay? Now, concentration for one container, yeah. And I'm going to assign you something like that. Okay? And maybe it's not going to be quite as simple as this, but, you know, first problem probably will be. Okay? With a little bit of a twist. So dq2 dt is q1 of t over v1 okay? And concentration is q2 over r times t. We don't need this to solve the equation, but we do need to know how to solve a differential equation that depends on a solution to another differential equation, right? So what we can say is the system of differential equations is dq1 dt equals negative r over v1 times q1 this. Pretty simple system, okay? But still, so it's going to involve a little more technique and a little more insight. Halfway makes sense?
I don't know where the Q1 over V1 comes from.
Q1 over V1?
Yeah. How's that the rate of change of Q2 with respect to time?
Well, first of all, the first equation is just this one, right?
Yeah, I get that one.
Okay? Yeah, and have to multiply that by R. That's the rate at which soap is leaving the first. There's the concentration times R, right? Well, that's the rate at which soap is going into the second, which is the rate of change of Q2 with respect to T.
Okay.
Okay? And what we want to find then is we want to find the